I'm Rowan. Thanks for hanging around for my talk, which is Securing GenAI in Finance. I'll discuss some AI threats and, most importantly, some tools and techniques to mitigate them. I'm head of security at Control Plane, so run the security team, which is our happy bunch of security engineers, architects, pen testers, DevSecOps specialists. I've been in the cloud security space for coming on to 10 years now as an architect and wannabe engineer across government, finance, and fintech. Prior to that, I did a PhD in neuroscience and sleep, which is a bit of a cruel irony given that I now have 2 small children. As for Control Plane, we're a cloud-native security consultancy with clients in regulated industries. We specialize in securing next-generation technologies. Speaking of which, within the AI space, my much smarter colleagues are currently involved in a number of initiatives. So we're a core part of the CNCF Technical Advisory Group for Security, which has recently shepherded Kubeflow through a security self-assessment. We're embedded within the FINOS AI Readiness Group, which I believe has been sort of discussed a few times today. And internally, we've got staff gathering AI red team experience, and we've got an initiative with some partners to come up with a AI security reference architecture, which I'll introduce at the end. So today I'm going to introduce the challenges that AI poses for security teams in the face of rapid adoption. I'll talk about the importance of threat modeling and describe some relevant threats. Then we'll examine some controls and some tooling that might be useful for control implementation. With the rapid rise of AI and machine learning tech, I think everyone is excited about the promised benefits in a variety of ways, from the ability to provide personalized recommendations to end users, to drawing conclusions from vast quantities of data in previously sort of unthought of ways to assist with fraud detection, credit scoring, making financial predictions, and so on. So given that set of benefits, there's quite the rush to adopt AI. And within an organization adopting AI, your stakeholders broadly look like this. Oh, where is it? There. This was all drawn with Google Gemini, so if I offend any of those stakeholders, it's not my fault, it's the AI's fault. The business is happy because it thinks it can do more with less, and it potentially gains a sort of advantage over its competitors. Product owners, capability owners are happy because they can potentially deliver capability more quickly and in ways they hadn't previously envisaged. Engineers and developers are happy as AI can help them do their jobs, as we saw in the last talk. Or they can leverage existing AI models within their code instead of building their own sort of bespoke pieces of functionality. But you need to spare a thought for your test teams, your security teams, and your legal and your GRC teams. These generative AI models are non-deterministic. They're sometimes hallucinatory and unpredictable, and they do present a whole new suite of security challenges. Your test teams now have to find a way of working to ensure the outputs of said programs are rational, correct, and work as intended within the business use case. Legal teams are worried about a whole raft of new inbound regulations, and ultimately they've got to manage the risks and potential legal challenges associated with AI-based decision-making, privacy concerns, and so on. And security teams now find themselves at the intersection of these 2 teams' sort of sets of concerns and a whole new raft of threats at the application layer. In addition, with the sort of rapid adoption of these LLMs and generative AI bits of software across an organization in a variety of contexts, such as code generation, you've now got a whole bunch of new threats and impacts in a variety of new contexts to deal with. So with businesses pushing rapid adoption, there's a chance that security teams do end up being overwhelmed and a little bit swamped. Now, there's a mountain of excellent resources available to security teams for getting started, but most of these do operate at a fairly generic level. There's sort of general guidance on governance. You might have some threat and control libraries that exist at a higher level. But for sort of your security engineers on the ground, understanding where to start, which risk to mitigate, and how to mitigate it can be a bit tricky. So, like any new system, we actually recommend everyone takes a step back and everything starts with a threat model. Threat modeling has become increasingly more prevalent over the last 5 or so years. It's the industry's acknowledgement that a compliant system is not a secure one, and to be honest, vice versa. Same applies. It also enables the ability to bring security conversations into the heart of the design and development process by shifting things left. It enables teams to focus on identifying the greatest risks to their specific systems and then mitigating them. And it's not actually hard to do or get started. You get your stakeholders in a room, some supporting documentation, and you answer 4 questions as a team. What are you building? What can go wrong once it's built? What should you do about those things that can go wrong? And did you do a decent job of analysis? i.e., do you think you'll mitigate the things you're worried most about? I'd recommend you split your model into layers of functions. So the application layer will have a whole bunch of new threats specific to LLMs. Your development and deployment pipelines, you should already have a variant of those, and you should already have an infrastructure or platform threat model that does address what controls should be in place should a hosted application be compromised. So for today, we're going to take the OWASP top 10 for large language models as our threat model, and OWASP have mapped these onto a generic architecture as shown here. You can see on the left-hand side the user interacting with a front end that calls the LLM, which then makes calls to plugins and onwards to downstream services to retrieve data or perform actions. So the top 10 is a list. I'll explain them as we progress and look at tooling and practices that security engineers can adopt to solve these issues. So let's start with the threats that exploit interaction with the model at runtime. Starting with prompt injection. That's the mechanism by which a crafty prompt is used to sort of bypass model safeguards, override system prompts to cause unintended actions. We're all aware of this. It's going to be the primary threat to address for some time to come when it comes to LLMs. Insecure input handling occurs when an LLM output is not scrutinized before being sent onwards to, for example, a backend system. An example of this would be an LLM returning code that's interpreted by the end user's browser, which results in a sort of cross-site scripting attack. Denial of service is where long or repeated queries to a model can consume a large amount of compute power, or if the model is externally hosted, like one of the OpenAI APIs, that'll cost you a lot of money. Sensitive information disclosure is when sensitive information such as PII is returned back from a sort of self-hosted proprietary LLM. Maybe your training data sets haven't been sanitized properly and so forth. That results in PI leakage outside of your organization. There's also an argument to suggest that, if you're using a third-party API outside your environment, queries that contain PI data being sent out of that environment is also PI leakage from the org. And finally, over-reliance is just a sort of an overarching warning against blindly trusting the outputs of LLMs as a recipient in a broader context, advising to sort of validate outputs not hallucinatory or contain errors before trusting or using it. I think we've all seen humorous examples of LLM-enabled chatbots recommending competitors' products and so forth. So given these threats and all the money flooding into the space, naturally there's now tooling that assesses the quality and security of inputs and outputs when the model's called. There are a few. MITRE and NVIDIA have published some work in this space. We'll talk about a couple of different examples today in terms of LLM Guard and Guardrails AI. They're open source tools. And we'll use LLM Guard for our example, not as an explicit recommendation, but it was just easy to get up and running, to be honest. The LLM Guard and Guardrails AI, they work as libraries that developers can embed alongside their code that makes calls to and receives responses from LLMs. We'll talk about the scalability considerations associated with that in a moment. So we're going to look at a very simple demo. We'll use an input filter to prevent the following attacks against queries sent to the OpenAI API. And you'll see how we'll mitigate against prompt injection, model denial of service, or in this case, wallet, and sensitive information disclosure, in this case, PI being sent outside the environment to the OpenAI API. And being a security guy, don't leave anything to chance. Just got a video at the moment. I think that's good. That's not visible, is it? You struggling to see that? Let me do it live. We'll do it live. Yeah, I mean, I've had enormous trouble with this, this AV setup already, so let's do it live. Maybe that's a bit better. Right. Is that better? People see that? Okay. Start off with a really, really simple Python program that calls ChatGPT. This is unprotected, right? You can see here, all we're doing is we're using the OpenAI libraries to call ChatGPT. The system message is something that's kind of not exposed to the user typically, something that bounds or is supposed to bound the prompt. And in this case, we see any topic outside of programming or AI is banned. But then within the prompt, we've got the classic ignore all previous instructions statement. And text rep's not on, but the Roman Empire never being that far away from my mind, I ask about the history of Julius Caesar. So obviously now run this. And naturally, that's the output we get. We get some output from the OpenAI API giving us some history of Julius Caesar. Now, more interestingly, if we then add the LLM Guard libraries to this, and I'm not sure we should expect all developers to do this, I'll talk about that in a moment, I can input a whole variety or add a whole variety of input scanners. So in this case, we configure a input scanner that looks for PII data. We've set an arbitrarily low token limit to stop long queries, and we've also got prompt injection detection with a threshold. We've got exactly the same model, system message, and prompt. And then running this. A whole bunch of output with LLM Guard debug info, and at the end you see there that the program throws an error. It's quite a simple program. The prompt's not valid. We've triggered PII detection. We've triggered the token limit. We've triggered prompt injection. Prompt doesn't go out the environment. So fairly simple demo there. Right, that means I can advance through this slide now, hopefully. Okay. So these tools, and there are others, do have a number of checks that can be used in some way to mitigate the OWASP LLM top 10 when it comes to sort of input and output from the LLM itself. For over-reliance, because the use of the LLM is kind of context dependent, acting as a chatbot, authoring news articles, code generation, and so forth, the mitigations will also be context dependent, but there are checks to detect for sort of competitors, relevance, toxicity, foul language, misformed queries, and so on. Let me acknowledge that actually it's my personal hatred to have sort of throw a tool at it security. So it rarely works well. Just adding a tool won't mitigate all of your risks entirely. There's lots of things to take into account here. This tooling is never going to be foolproof. It's not going to mitigate all your risks. It's important to note that the checks enabled by these tools are often using LLMs under the hood themselves, gives you a bit of a supply chain issue. You've also got to test the efficacy of these, which also depends on your ability to comprehensively test LLMs. You'll notice that for the prompt injection, I set a threshold. So you're going to have to do some threshold tuning to ensure that detection and blocking occurs without causing false positives. And you've also got to make some decisions about how you're going to bring the tooling in and actually run it within your estate. Do you rely on developers to import libraries, write the checks themselves alongside the code, keep all of that up to date? Then, in order to filter or in order to monitor the performance of the tool, you've then got to filter the application logs to get the tooling logs out. So if you've run containerized environments and you're familiar with the service mesh argument, it's a repeat of that, right? You've got the opportunity potentially to to force inputs and responses through proxies that are centrally managed to conduct checks. It allows you to have some central manageability, possibly a simpler logging stack, and the ability to run in various topologies such as namespace, node, or cluster. Finally, LLMs are clearly not lightweight. So you've got to think about the disk space and overall impact on application performance before they're used. And actually, some of the checks within these tools do have sort of benchmarking performance criteria with them. So there's still work to evaluate and figure a lot of this out. Switching to supply chain security threats, and those threats will also apply to the tooling I've just mentioned. Supply chain vulnerabilities need no explanation. We're talking about the security of software that comprises the model, third-party libraries, training data sets, and so forth. Training data poisoning is a subset of this, specific to ML models. Should your infrastructure permit tampering of data sets or data set selection, sanitization, or preparation process just not be thorough enough? Supply chain security, I think you'll all recognize, is incredibly important, but continues to be a unsolved and maybe unsolvable issue. There's enough content and discussion in the space for many talks, many times over. But to split it broadly into two components, it's the security of the infrastructure hosting your build and deployment pipelines, and the security features enabled within those pipelines, ensuring that your code or your model is secure. And you can't have one without the other. You can have the greatest artifact signing infrastructure in the world, but if your key signing infrastructure is being compromised, you're toast. It's worthless. Most of these controls are well documented. So for today, we're just going to focus on scanning, testing, and the importance of a bill of materials for AI models. There's a few tools for running vulnerability scans against LLMs, such as Garrick and Giscard. We'll just talk about Garrick today. It can be run against OpenAI, Hugging Face models, and local models in the GGML format. There's a variety of probes that test for various sort of prompt injection and Dan-like attacks, continuation attacks, where it tries to get the model to continue to use or respond with an undesirable word, and then more importantly, attempts to have the model generate code for building malware, and attempts to make the model hallucinate support for misleading or false claims. Now, Garrick outputs provide machine-readable outputs, JSON, so you can integrate them within a pipeline. The tests are quite long to run, which does preclude a demo. Otherwise, we'll just be here for the remaining 10, 12 minutes. But for all of the tooling and things we mentioned today, we'll make demo scripts available in the control plane GitHub shortly. In terms of testing, the better your testing is, the better you're going to be able to detect whether the behavior of models that your software is dependent on has changed. And that could be the result of just the model evolving and no longer being usable for you, but it could be also the result of model tampering or training data poisoning. It's really, really important to get testing right early on, and it prevents model over-reliance, right, where the business gets bitten by models that produces unwanted outputs, such as chat apps that recommend a competitor's product. Prompt foo is a really good way of creating tests to validate the output of models are correct. I did have a live demo lined up for this, but then I realized it did output my OpenAI API key, which, despite only having $15 on it, I prefer to keep it my $15. So got a couple of screenshots instead. This is the configuration of a test here. We're looking to make sure the answer to the question, how many chemicals exist in cigarettes, is just a number. And we assert that with some regex at the bottom there. We'll get prompt foo to run that query against, you'll see at the top, GPT 3.5 and GPT 4. And bear in mind, you can then run prompt foo against your own custom models. So in future, that might be between your existing model and your latest version of your model. Via the UI, you can see here that despite the prompt only asking for a numeric response, the GPT 3.5 model was unable to pass the test because it's got the word chemicals in it at the bottom there. So that's really, really powerful in terms of detecting changes within models, regardless the reasoning behind those changes. I really strongly do recommend you adopt a comprehensive testing with this type of tool to ensure your model works as intended, both from a business use case and security perspective. Here's the obligatory bill of materials slide that's in every talk at the moment, except this one's about AI bombs. It's an emerging concept on top of an emerging concept, given that the software bill of materials thing is not mature yet. There are multiple frameworks and schemas, the SPDX AI bomb, the ML bomb. There's been some really good work done by Jason Bell and Omar Santos that's quite influential. AI bomb is going to be fundamental for many things, including establishing transparency and trust within AI systems. Within the sort of supply chain security space, these are always obviously going to be critical in understanding what makes a model, what makes up a model in terms of data sets, how the model is constructed, usage and limitations. So in the event of a poison data set being used, the ability to identify models that leverage these will be critical. Just very quickly to finish the 10, and I realize we are pushing up against time a bit. Insecure plugin design is just focused on ensuring that the reader of the OWASP top 10 treats LLM outputs as untrusted and creates secure LLM plugins themselves. So plugins are these pieces of code that are called directly by the LLM, and then they have an onward effect of command sent to downstream services. I think within the OpenAI UI, you could just code these in, and that resulted in a whole bunch of insecure plugins being generated where, you know, the plugins weren't subject to appropriate controls. So those controls would be, they're just basically APIs, right? So mitigations are good API security practices and application layer controls to protect them, such as input validation and parameterization, enforce authentication and authorization following least privilege processes, and build your plugins within pipelines and subject them to appropriate DAST and SAST testing before you implement them. Excessive agency, and there's a lot of these that then overlap sort of downstream of the LLM, once again is warning us against allowing LLMs to directly interface with other systems with excessive permissions, autonomy, or functionality. So should the LLM create ambiguous or unexpected output and can all of a sudden utilize excess privileges or functionality within plugins or downstream services, you get a whole bunch of unintended consequences. So once again, treat the output of LLMs as untrusted. Ensure the plugins and downstream services called are hardened appropriately by ensuring the LLM can only call the plugins and downstream tools it needs. Make sure those plugins only have the functions that are required, and those functions aren't open-ended, so just don't get your plugin running shell commands, for example. Ensure the LLM plugins and tools have limited permissions themselves on downstream services. Enforce authorization and authentication throughout the stack. Don't just blindly assume that the LLM or the end user can perform the action requested. If you've got sensitive actions, like you're relying on an app like this to author tweets or create public-facing web pages, just consider using a human in the loop, right? Finally, model theft is where the model is extracted, either through carefully crafted inputs via the UI by the end user, or just extracted from the estate owing to misconfigured or insecure underlying infrastructure, whether that's your code repositories, build, training, or runtime infrastructure. So ensuring your infrastructure controls are in place, including code repos and training environments, are hardened is important, as is looking to secure the interface through which end users consume the application. You can consider API rate limiting, and if you're very mature, you can look at monitoring and auditing, or specifically monitoring in real time your front end to look for sort of weird traffic coming in, but you need a good level of maturity to be able to do that. So in summary, threat model your AI workloads. That will give you new risks to think about at the application layer. Make sure you maintain the threat model for your runtime infrastructure, which could be designed with controls to cater for a compromised workload, regardless of whether it's an LLM application or not. Keep testing your models rigorously to ensure they behave as expected, although you may need to adopt new techniques and tooling, such as a prompt foo demo today. and always treat LLM outputs as untrusted. Seek to validate, authenticate, and authorize requests made by LLMs as often as possible and throughout the whole stack. And also should be aware of the ecosystem of specialist LLM security tooling and scanning that's developing. Finally, we're trying to put our money where our mouth is. We're trying to combine all of this knowledge and more into an AI security reference architecture, where we'll put some of the things today into practice. We're doing that with some partners at TestifySec and Helix. And it'll be useful for us to get some experience and understand how things are going to go in practice. Okay, thank you very much. Got 1 minute for questions. Yes, please.
I'm curious, how do you use AI boom in a world where everything's changed? AI provides the change the infrastructure, do the patching, change the libraries. How do you use it? Whatever you get might not be an accurate snapshot of the system that you will be using for the day.
Yeah, so I've always come from the container space where once the container's built, it's immutable, right? So I'm kind of sitting in the space where I'm looking at deploying things like Helix ML in containers on Kubernetes. The container's immutable. When I'm looking at AI bomb or SBOM within that context, those are things I'm looking at. So it's fair to say there isn't a mature implementation at this point that covers every use case. So yeah, it's a good point. Anything else? Okay, thank you very much. Cheers.